Okay, question 3 of the December 2014 paper says it's all about backgammon, but really it's nothing to do with backgammon, it's just about dice. So it says, Anna plays backgammon in her free time. Backgammon is a board game where two players, in turn, throw two dice. The dice throws decide how many spaces the players may move their pieces. If a player gets a dice throw where the two dice show the same numbers, a double in other words, the players may move twice as many spaces as shown on the dice. What is the probability that Anna gets a dice throw where the two show the same number? Well, whenever you have a problem involving two dice, it can often help to do a little table of the possible outcomes. So 1, 2, 3, 4, 5, 6 on one of the dice, and 1, 2, 3, 4, 5, 6 on the other gives you 36 possible outcomes. And then you can see clearly from the table that a 1 and a 1, a 2 and a 2, 3, 3, 4, 4, 5, 5, or 6, 6. There's 6 possibilities out of 36 where she gets the same on both. So looking at it that way, you can say it's 6 out of 36. Or another way you can look at it is she throws the first one, and it doesn't really matter what that first one is. It can be a 4 or a 5 or a 1 or anything. All she's worried about then is the second one matching it. So there's a 1 out of 6 chance that the second one will match the first one. So I've written probability, C attachment, and then I'll have a table like that on a supplementary sheet, clearly labelled. Probability is 6 out of 36, which is of course the same as 1 out of 6. Part 2. Anna is considering how many different dice throws she can get when she plays backgammon. A dice throw can, for example, be 3 and 4. It makes no difference which of the dice is 3 and which is 4. So in other words, in terms of the game, a 3 with a 4 or a 4 with a 3 is the same thing. Investigate how many dice throws Anna can get in backgammon. So again, I've got my table, and this time I've grayed some of these out because some of these are the same looking at it in those terms. So a 2 with a 1 is the same as a 1 with a 2. So because I don't want to count those twice, I've grayed some of them out. So I've got a 2 with a 1, but not a 1 with a 2. I've still got all of the ones that are the same. So 1 with a 1, 2 with a 2, 3 with a 3. So in total, that gives me 21 possibilities. And a lot of people, when I marked this, realized that it was 6 different ways where it was a 1 with something, and then 5 different ways where it was a 2 with something else, and then 4, 3, 2, and 1. So I saw a lot of people answering this with 6 plus 5 plus 4 plus 3 plus 2 plus 1 equals 21. What I actually did was to list all of the possibilities systematically. Didn't take me too long to do that. As you can see, I've got a quite good system to it, so there's a pattern to what I've written, and it's 21 throws. Question 3.3. Anna often plays backgammon with Jonathan. He claims that it's more likely to throw dice where the difference between the two dice is 2 than it is to throw dice where the difference between the two dice is 3. Is Jonathan right in his claim? Give a reason for your answer. Well, again, I've got my tables. Now, there are 8 ways out of 36 you could get a difference of 2. For example, a 3 with a 1, or a 1 with a 3, a 2 with a 4, or a 4 with a 2. So on the 2 dice, there are 8 ways out of 36 ways that you could throw 2 dice where you can get a difference of 2. So there is an 8 out of 36 chance of that happening. Doing a similar thing for a difference of 3, that you can see that there are only 6 ways out of the 36 ways that you can throw 2 dice, where you get a difference of 3. So you could get a 4 on the first one and a 1 on the second one, or a 1 on the first one and a 4 on the second one. And the table shows that there are only 6 ways that that can happen. So the probability of that happening is only 6 out of 36. So for my answer, I've written the probability of a difference of 2 and then C, the attachment. Then I'll have all of these tables neatly on a separate sheet, clearly labelled. That probability is 8 out of 36. And then the probability of a difference of 3, again, see the separate sheet, which I've clearly labelled, hopefully, is only 6 out of 36. And then having done the 2 calculations, make the comment, he's right. Question 3.4. Anna thinks that her and Jonathan are just as good at backgammon as each other because they win just as many games each. They've agreed to play 3 games of backgammon. How big is the chance of Anna winning all 3 games? So what that information is supposed to imply is that the chance of her winning a game is a half. So the chance of her winning 3 games in a row is a half times a half times a half, which is 0.125, or an eighth if you're doing it in fractions. So setting that out neatly, it looks like that. And the marks are 4, 4, 4, 4.